Hi everyone, how are you doing? Okay, so today just consider this class as a very first class of your machine learning, which means that even though we have covered least square solution, in those that kind of learning will be helpful. But you can still consider that okay, whatever you have studied. Let's suppose that you have not got anything from those lectures. Okay, I'm assuming. Okay, let's suppose you have not got anything, so you can consider this lecture as a formally a first lecture of machine learning. So whatever we have seen was related to more of the the linear algebra, related to more of the linear algebra or the calculus. But now we are going to start formally machine learning. Okay, so we will have everything step by step. Let's just get started. Okay, so maybe before we start, let me just tell you something. Okay, okay, just a second. I have those slides in between, but I thought that okay, I can just tell you before uh, before starting the slide. Just a second. Yeah. Okay. So a disclaimer is that this course is not just for Gate D aspirants, which means that if you are thinking to transition into machine learning, then also this course is going to be very much useful. Okay. So for example, we will ensure in this course we will ensure sorry in this course we will ensure that that if you want to transition into the machine learning field, then also this course will be extremely useful. I don't know what is happening. Just a second. Okay. So sorry about it. So what I was saying is that this course is not just for Gate DA aspirants. It means that it is for the Gate DA aspirants definitely, and we will be solving many Gate DA relevant questions, which will eventually help you to understand machine learning in a thorough way, which means in very depth. So even if you are not Gate DA aspirants, then also this course is going to be very useful. Okay, so definitely if you're preparing for Gate DA, this is the course, right? Here you will be getting everything which whatever is required for Gate DA. But I'm just telling you the other way around, which means even though you are not preparing for Gate DA, still this course is going to be very helpful. We will ensure that you learn machine learning thoroughly, enabling you to directly apply for the machine learning jobs if you do this course. Even if you're looking for the transition into machine learning field, you will find this course extremely useful. We will also provide practical assignments and projects focused on the machine learning algorithm. Again, note that these assignments and the projects that I'm talking here are not required for Gate DA preparation, so you can skip them if you prefer. So we will be having optional classes for the assignments and projects. So that I will not be taking because I want to focus on the theory part, and we have a few other folks from IISc, so they will be designing the assignment and projects and will be presenting to you. Obviously, I will be having the back end involvement, but not on the front end. Anyway, I'm just telling you that we will be having assignments and the projects as part of this course, but those assignments and projects are not required for Gate D preparation. Okay, so you can skip them if you prefer, or you can complete those assignment and projects, which means that those won't be too heavy to understand. So if you want, you can complete with us, or maybe after the Gate exam, or work on them with us. Okay, to gain a deeper understanding of machine learning algorithms. So whatever we are going to see in this practical assignment project, if you want, then you can skip those and you can do them later on, or you can do them with us. They will not take much of your time. Okay, if you have, let's suppose, time, and you think that okay, you want to understand how the practical things are going to work, then I will suggest you that if not all of them, you just do one or two. Okay, so you just do one or two assignment or project with us, and then you can complete the remaining later on. Just do one or two so that you get to know that okay, how the theory is getting converted into the code. That is the only reason you can just do one or two with us, and later on you can do rest of them, right? I hope you understood. And if you want, like, then you can do all of them with us. It's good. It's not going to harm you. So I hope this is clear that it is not just for Get D aspirants. It is for you if you even want to transition into machine learning field. Also, about the prerequisites, because there are like many questions that I'm getting about it. You can feel free to start this as your first course. which means that even if you have not completed linear algebra, calculus, or probability, then you can feel free to start this as your first course, right? Definitely you can feel free to start. But at the same time, while a basic understanding of linear algebra, calculus, and probability is helpful, so if you have already completed those, then it is definitely going to help you here. We will cover the necessary topics. So for example, if let's suppose in linear algebra projection is needed, okay, so I have already covered the projection as a part of this particular series. So if whatever is needed, whatever is necessary, we will cover those along with the course. Okay. Uh, don't worry, those who have covered this linear algebra, probability, and calculus, don't worry. There won't be too much of the repetition. It will be just like, in every 5 6 hours, I will just spend maybe 20 to 30 minutes. Okay, 20 to 30 minutes to recap the things, or to tell you on average, I'm telling you, okay, in every 5 6 hours you will find that, okay, 20 to 30 minutes will be there to cover the basics from linear algebra, sometimes from calculus, sometimes for probability. Okay, so you can feel free to start this as your first course. Great. With this, let's just start the course. What is machine learning, right? About the machine learning. Great. So let's just start with the question that what is a machine learning. Now, let's just first see that what is learning, and then we will see what is a machine learning. So the basic definition of learning from any dictionary, or you can say from any English literature, you will find that the activity or the process of gaining knowledge or skill by studying, practicing, being taught, or experiencing something is called learning, right? I mean, all of you know what is learning. So just it is called basically learning is a process of gaining knowledge by practicing, studying, or being taught, or experiencing something. What is machine learning? Machine learning is one term which actually has very vast definition, in the sense that there is no fixed definition. Everyone, there are many pioneer in machine learning. Everyone has tried their own way to explain the term machine learning. But in simplistic word, you can say that it's for many problems, it's difficult to program the correct behavior by hand. Okay, machine learning does what? It is an program. It is an approach, or it is program and algorithm to automatically learn from data or from experience. So basically, it is some kind of you can say program, uh, or some approach to program an algorithm that automatically learn from the data. So what do I mean by automatically learn from the data? That you will get to know. Okay, so it is some approach that enable the machine to automatically learn from the data. And now you might be having the question that why might you want to use the machine learning algorithms, right? I mean, why you want to learn automatically? Okay, so little bit you might have understood that what is machine learning. It is a process to automatically learn, right? But why do we want to automatically learn, and how can we automatically learn? So these are the definitely two questions, right? So let's just see that why we want to even automatically learn the things. For example, right? For example, let's suppose this is one picture which is in HD. Mostly it is in HD, which is higher dimension. This is, let's suppose, given this picture, if I ask you the predict the word species depicted in this given picture or given image, which means what kind of word it is, right? This is the question that we are posing to you. So this is just one question. There could be many other questions. For example, the problem is like this, that you have you have some English text and you want to translate that to a French text. This is, let's suppose, a different kind of problem. So the first kind of problem is that you want to predict the bird species. The second kind of problem is that you want to have the translation from English to French. Okay. The third kind of problem could be, I mean, there could be wide range of problems. I'm just giving you two, three examples. The third kind of problem is that given, this chess board, you want to predict the win probability, okay, of a given move in the given game. For example, I think it was white to move, and white has just placed his or her king from here to here. Then what is the probability that if the person move his king from here to here, then what is the probability of winning after this move? Let's suppose this is one another kind of question that we are asking, right? So there are like two three questions. Just for the sake of example, I have posted to you. So how to solve these questions? Let's just see how to solve these questions without machine learning. For example, if you want to classify the bird, right? Then what you need to do without the machine learning, you need to probably hire bird expert to teach you about different birds. For example, we have one of the bird expert here in the chat section. He's saying it's blue sparrow. So we need to hire him or her for the bird classification, which means that what kind of bird it is, right? So we need to actually hire some bird expert, and that bird expert can tell you that what kind of bird it is, right? By looking at the, so what the bird expert will do, he or she will look at the beak shape, feather colors, and a typical environment and many other things, right? And based on that, he will tell you that what kind of bird it is. Similarly, let's suppose I want to do this translation without, let's suppose, using machine learning. Then I mean, you can typically program it, but generally the normal algorithms doesn't work so well. So what you can do, you can ask any machine learning sorry, any language translation expert, translator, and then that person can convert the given English to French. Okay. Similarly, if you want to predict that what is the win probability, then what you can do, you can maybe probably hire some, you can say some grandmaster if you can afford, right? Definitely. And you can ask him that what is the win probability, because he has to be very much expert, right? To tell you probability very accurately. So the thing here is that if we want to do all of this, probably we need to take the human help, and human help is not very convenient because you have to set up an entire team to find out the bird expert, and then you need to test it whether the bird expert is good enough or not, and then finally you need to hire, and obviously it's not worth doing all of this. And even though you have you bird expert with you, or you are yourself bird expert like Ijaz, okay, then also you have to spend a lot of time for every image, right? I mean, you can't do it in fraction of seconds, or you can't do it in fraction of minutes, right? You have to spend a lot of time. Let's suppose there are 1 million images. So Ijaz, can you tell me, given 1 million images, how much time you will be taking, how long you will be taking? Probably you will be taking a lot of time, right? So obviously it's not worth to spend that much time to solve those kind of problems, and neither we can afford to spend that much time. So that is why machine learning is very helpful to do many of the tasks, right? Uh, I mean, whether it is just image classification or the machine translation. Machine translation is one typical word, by the way. We also call it language translation, but machine translation is one word that we use in machine learning for the language translation. Okay. Anyway, so whatever kind of task it is, you probably be taking the help of machine learning to solve it faster, to solve it efficiently, to solve it in the fast manner. So that's why definitely, as all of you know, that machine learning is very much useful. Okay. So this is the picture without the machine learning, which means that without the machine learning, you have very specific instructions. For example, if you want to translate one language to another, then probably you will be writing some set of rules, right? Let's suppose let's suppose I'm not French expert, but okay, so probably has this translation in French, which is Montrage. So you will be saying that if show, then it will be Montrage, right? But do you think it is very much convenient? Because probably the word order might be, shuffling. So here it seems like it is one-to-one mapping. Montrage, this is, I think this is us. This is for the, this is the article that we use in the French. Uh, and then documents is just documents, I think. Okay. So if you can write if and then and these things, but obviously it is also not very much convenient. Why? What is the reason behind it? Yeah, it will be very long code, or also it is not very useful, in the sense it is not very convenient, in the sense that there could be the reordering of the words, right? It need not to be, for example, if I'm saying in Hindi, I don't know any other language other than Hindi or English. So that's why I'm just giving the example of Hindi. Let's suppose I'm saying मैं घर जा रहा हूँ, है ना? मैं, ठीक है. Okay, if I'm saying something like this, then I think in English it will be I am going home. right? So as you can see, the word order is also getting disturbed. So basically ghar, which means home in English, it is the second word here, but it is the last word here, right? So there could be many of the problems with the fixed and static code. Obviously you can come up with the many rules, and then you can finally have the machine translation or the language translation, but it is not very convenient, as you can see, right? So that's why machine learning is useful. So that's why we are saying here the very specific instructions should be there. Very specific means the code will run in a fixed way, right? It will be like if and else, if this, else this, like this, right? So the code will run in very fixed way. But with machine learning, you can pour the data into it, which means if you have, let's suppose, supervised setup, then you can pour the data. For example, you can have both of the things. मैं घर जा रहा हूँ and I'm going home at just one pair. This is, let's suppose, X, this is Y. Okay, this is your input, this is your output, this is your input, this is your output. Okay, you can pour this data, input output pairs, in the machine, and the machine will automatically get to understand somehow. Obviously, like, we need to train it, we need to have a very good model and so on, but somehow we will make sure that machine is able to understand that, okay, मैं घर जा रहा हूँ is corresponding to I'm going home. So if we give any other Hindi sentence to it, then probably he will be doing the correct translation. Okay. I mean, the better the model, it will be doing the correct translation. The better the translations are. So here we just need to pour the data. Here we need to show the machine learning the data, and then we need to write basically very specific set of instructions. So the use of machine learning is that we don't need to write very specific, you can say, the instructions. Machine learning will take care of it, right? Machine learning will recognize the pattern. Understood? So machine learning is there to recognize the pattern. Basically, the another name of machine learning is also called as pattern recognition. In fact, there is a book which is a very famous book, and the name of the book is Pattern Recognition. Anyway, the machine learning, pattern recognition, these terms are, many people use them interchangeably. So don't worry about it. I mean, machine learning is just recognizing the pattern. You can say like this. Okay. So there are many machine learning algorithms to start with. So there are very large number of machine learning algorithms that computer scientists have designed, which all generate models using different approaches. How do we choose one to use? So there are many algorithms. We need to basically, as a machine learning engineer, we should be having the good intuition, or we should be having, good expertise to select one of the model. Okay, this model might work well. Obviously, we will be doing multiple experiment. For example, given a problem statement, you will be applying linear regression. Probably you will be also applying, let's suppose, SVM. You can also apply any other model, and then finally you can say that, okay, this model is working fine, this model is working great, so let's just use this model. You can definitely do it, but you should be also having the good intuition that, okay, this is little complex, so maybe linear regression might not work or something like that, right? Okay. So we can break algorithms into the groups. Let's just see that what kind of groups are there. So what you can do, you can divide the machine learning algorithms into three types. One of them is called supervised. Okay, based on the data. Machine learning algorithms, you can divide them into three types. One of them is called supervised. Another one is called unsupervised. And another one is called RL, reinforcement learning. So anyway, this reinforcement learning is not generally taught, neither it is needed for most of the tasks. So you can, I mean, obviously it is very useful, but for most of the tasks, you can just ignore this reinforcement learning. And also it is not in the GateDA syllabus. And not just GateDA syllabus, even if you do masters at that level also, you will not find that people are studying this RL too much. Okay. And also, like, very rare, I can say very rare people do PhD in RL. Mostly do PhD in general algorithms like supervised and unsupervised, right? They never touch RL. So RL is not much useful for us. So neither it is in the gate DS syllabus. What is supervised? If you have XY pair, maybe from the least square. I have already told the least square just to give you the slight, introduction to machine learning. That what is, x and what is y, in the sense that you have your x in the least square and you have your output y, right? So that is called supervised if you have x and y. Unsupervised, basically here you don't have y, so only x is there, right? Only x is there. Some people also have one more field which is semi-supervised, or some people also call that unsupervised. Semi-supervised is something where you have few xy. I mean, you have few pairs of xy, but few most of the pairs are of x only. So you can somehow make use of those few pairs to know more about the data, and ultimately you have to apply the unsupervised learning algorithms. So that is called semi-supervised. Anyway, let's not get into this because it's not required. Okay. So based on the type of the data, you can divide it into two parts: semi-supervised and unsupervised. Let's not worry about RL, right? So one of them is called one of them is called supervised and one of them is called unsupervised. Supervised means you have X and Y both. Unsupervised means you don't have Y. This is based on the data. There are other type of classification or other type of divisions possible. Okay, based on the type of output. We will see today what is regression, what is classification. Least square problem was regression or classification that we have seen. Least square problem was a regression problem, right? Okay, some of you might know it that it was a regression problem. We will anyway see the definition of regression and classification. So based on the output, based on this by some people classify as regression classification based on the type of model that we will see later on. Okay, I think in gate D also there was a question this time, generative and discriminative classifiers. Do you know this? There was a question in gate DA this time. Like what do we call it? Match. मतलब यहाँ पे they have given you, for example, some machine learning algorithms. For example, one of them was naive Bayes. Okay, one of them was logistic, and then they were asking naive Bayes is basically, let's suppose P is discriminative, okay, and Q is generative, and I forgot C, what was the C option, I forgot. Similarly R here, but yeah, so they have given you one question, what is discriminative, what is generative classifiers. Anyway, so based on the type of model you can just classify that into two types: one is generative, another one is discriminative. Okay. Now, let's just see that what is basically supervised algorithm more in the more detail. Okay. Or let's just see in general. Let's just first try to understand what is supervised and unsupervised. Okay. So, Jew of ML problems. So, for example, if we talk about the supervised algorithms, then here we have data and we also have labels with them, right? Data and labels both are there. And this ML algorithm does what? As we have seen in the least square also, it does the prediction, right? It learns the function. Particularly, do you remember it was learning ax plus b? It was learning what? Can you tell me? Yeah, parameters. So what were the parameters? A and b, right? It was learning the parameters in the least square. We were learning a and b, right? So that's why I have already told you least square just to understand the basic definitions here, right? Okay. So supervised means you have X and you have Y. So since it is just introduction, you might or might not get it. So don't worry about it. Once we actually, let's see, there is no way to understand this fully unless and until we start the supervised algorithms, right? So for now, just take it on a lighter note, in the sense that even if you are having some doubt, even if you're not understanding this fully, that is fine, because there is no way to explain this unless we start actually the algorithms, right? I mean, I can just tell you that, okay, there's a data, there's a label, but to understand them fully, we have to actually start it. So don't worry, even if you have not understood the definition of supervised. Overall, I can say you also have the labels, just like we had in the least square. Okay, I hope that is fine to everyone. In unsupervised, we don't have the labels, so it is without the labels, which means we don't have by. Then what we are doing, if we don't have by, then what we are trying to do here, we are just trying to learn the representation, in the sense that where does this particular data point lie in the space. Okay, let's suppose this is a space of Rn, which means the data point that we have. Okay, you might not be able to understand, but let's suppose there are n features, x1, x2, and there is no by. Okay, I mean there is no by. By is not present here, but yeah, there are n features. And every of this point, let's suppose this is the first example. Okay, first house, you might have seen house prediction. I have already given one example of house prediction. So number of square feet, number of bathrooms, number of bedrooms, like that, right? So this is, let's suppose, the n features. So this house prediction data is in Rn. Now we actually need to so you can you can probably understand this little bit. We actually need to understand the representation of the data, in the sense that, suppose, in the house prediction, okay, you have few features and you don't have by. Okay, you have few features. For example, let's suppose number of square number of bedrooms, okay, square feet, and so on. So let's suppose this is 3, this is, let's suppose, 2000 or whatever, right? So suppose you are representing the data in, let's suppose, 1, 2, 3, 4 dimension, right? So there will be 4 dimensions. Obviously I can't represent in the 4 dimension, but I'm just telling you, let's suppose there are 4 dimensions here. Suppose you are representing this house, let's suppose this is house number 1 here, and the similar house is there which is having, let's suppose, 3, maybe here this is 1800, and almost similar. So if it is 3, then let's suppose this is, bedrooms. This is the feature which is representing bedrooms. So if it is 3, 1, 2, 3, earlier was also 3. Let's suppose this is 2000. Okay. So 1800 will be somewhere here. So the next point will be, let's suppose, somewhere here, right? So it is close to the previous. Do you agree? If the data is almost same, then the representation will also be closer in the RN space. Do you all agree with this? Right? So the underlying assumption here in the unsupervised is like that we have I mean, if the data, or if the data points are similar to each other, then they're also closer in the RN space, okay, or the input space. Then what we will be doing, we will be just doing, I mean, the clustering is one of the example. Okay, we will be doing let's suppose clustering, which means we will say कि ये तो premium house है. Okay, for example, this is house category A, or some premium house. Okay, you can say this is cluster number, or maybe house category number. Okay, so this is cluster A. मतलब ये बहुत ही प्रीमियम हाउस हो गए, ये लेट सपोज लग्जरी हाउस हो गए, ये लेट सपोज ऑर्डिनरी हाउस हो गए. सो बेसिकली देयर विल बी डिफरेंट डिफरेंट क्लस्टर्स एटलीस्ट आई कैन मेक, कि दिस इज वन काइंड ऑफ द थिंग, दिस इज अनदर काइंड ऑफ द थिंग, दिस इज अनदर काइंड ऑफ द थिंग. फॉर एग्जांपल आई कैन से कि okay, these houses are similar. Maybe I don't know, actually, maybe they're premium, they are not premium, let's suppose, I don't know. But these houses, at least I can say, these houses are similar to each other, these houses are similar to each other, these houses are similar to each other. Can I say, just by representing them in the RN space, at least I can cluster them, and I can say, okay, house number 1, house number 5, house number 10 are similar to each other. At least I can say something like this, right? Is this okay to everyone? Okay, and let's suppose there is new house that is coming to you. You will also represent it, and let's suppose the representation of new house is coming here. Okay, this is some new house. So what you will say, this new house is in which cluster? It is near to which cluster? Cluster A, cluster B, or cluster C? It is near to cluster A. So you will say, see, you are telling me new house. I cannot tell the exact price of the house, but I can say it is similar to house number 1, house number 2, house number 5, and house number 10. At least I can say it is similar to this cluster. Okay, I will say it is falling under this cluster. So if those houses are premium, this is also premium. If those houses are not premium, this is also not premium, like that, right? I mean, I can just say, I mean, in the unsupervised, then or in particularly in the clustering, I can just say that, okay, this is in which cluster, or this is what kind of house it is, or what kind of data it is. It is similar to which, right? Okay. So Samir, please don't jump. Let's just have in the flow. Okay. If you already know machine learning, that's okay. Like, let's just have in the flow. And if you have any doubt later, you can ask, right? Okay. So is this clear to everyone? And one of the example that you can have, let's suppose you are reading a newspaper, right? There is a newspaper page. That page, sometimes, like, we have the dedicated page. For example, let's suppose this page is of sports, right? Or this page is from the political news, or maybe some Bollywood news or something like this, right? Let's suppose this page is either of this category. I mean, you don't have the name. Okay, you don't have. I'm not saying you have the name. You don't have the name. This page is of one of the category. So what you can do, you can have those pages, right? You can have those pages here. You can say that, okay, I have many pages, and if this page if this page representation is here and this page representation is also here, then probably both of the pages are similar to each other. Either both of them belong to sports, or both of them belong to political news, or both of them belong to Bollywood, or both of them belong to Hollywood, or like that, right? Or both of them belong to entertainment. So basically, in the unsupervised, we just say that, okay, things are together. For example, in clustering, unsupervised also have different algorithms. For example, you can say dimensionality reduction, clustering, like that, right? So there are many algorithms in unsupervised also, but one of the popular example of unsupervised is clustering. Are you getting little bit that what is unsupervised? At least we can just say that, okay, your data is similar to other data. Okay, that's all, right? We can represent them, and we can say, okay, this data is similar to this particular data, or this house is similar to this particular house. Something like that we will be doing in unsupervised. Anyway, like, we will see the unsupervised later on, because that is in the gate DA syllabus. But for now, we will be doing supervised, right? Okay. So one of the popular example of unsupervised is clustering. This is unsupervised. So today, and much for this course, we focus on supervised learning only, because this is the heavy, and this is, you can say, the major part of the syllabus. And not just for the gate DA, in general, for the machine learning also, the supervised algorithms are heavily dominated, because mostly we are having the label. Okay, in most of the cases we are having the label. If we don't have the label, definitely we will be going for unsupervised learning also. Yes, this means we are having a training set, and training set consisting of input and labels. So basically, we will be having X, input means X, and labels means Y. Okay. In case of supervised also, we have two type of algorithms. One is called classification, and another one is called regression. Okay. So the categorization is like this. You can say machine learning algorithms. Okay. Let's not worry about RL. We have supervised and we have unsupervised. In unsupervised, we have the popular example, which is clustering, right? In supervised, the popular examples are classification and regression, right? Okay. Now, let's just see what is classification, what is regression. So supervised is of two types, classification, regression. For example, if we have data, or the output level by in the discrete variable, which means these are the fixed. Let's suppose the categories are 1 2 3, like that, right? For example, given the image, okay, let's suppose this is the image which is given, whether it is cat or dog, or maybe there are multiple examples. For example, this is a bird. Okay. So if we have fixed category, let's suppose three categories, then we have classification. But if we have, let's suppose, continuous variable, can you give me the example of continuous variable here? What is the first example we have seen? The first example here we have seen in the least square. Anyone remember? Please don't forget it. Ice cream, sale, prediction, right? House, price, prediction. These kind of things are called regression. Okay. If we have real values, stock market, right? Stock market example. Yes, that is correct. Okay. For example, depending on your basically choice, right? You can have for the same data, almost same data, you can have regression or the classification. For example, the data is here, age and income. Here also age and income, the same data. But let's suppose you're interested with this data, you're interested in the classification, and you have these levels. So you can call it as a classification because this is rejected or approved. Okay. So if this is the age and income is this, then should we give a loan or not give a loan? It is rejected or approved, right? So you have this level, then it is called classification. For the same data, if you have this level, that okay, what should be the loan amount? Then it is called regression. For example, here rejected is represented by zero. I mean, in case of regression, you can try to predict with the zero. Approved, and then you can actually try to predict, okay, what is the approved amount. Are you getting the thing what I'm trying to say? So for the same data, you based on your use case, you can treat it as a classification, you can treat it as a regression depending on this by level. If this by level you are treating as a continuous, I mean, if you're writing the numbers here, you can say it is regression. If you're writing some categories, you can say it is a classification. Okay. So here in the classification, X is discrete, and in the regression, X is sorry, by is discrete, and then the regression by is continuous. Okay. One of the example we have already seen of the regression, that was ice cream sales prediction, right? So for example, in case of least square, sorry, there is one key. Okay. So in case of least square, this was our first example, ice cream sale prediction. So this is the example of regression clearly, right? We have predicted the line here, or we have predicted the A and B. Anyway, if you have not understood the least square, that is fine. I'm not expecting you to know it too much. Don't worry if you have not understood the least square. Okay, it is perfectly fine. I'm just telling you it is the example of regression. One of the example of classification, or one of the classic example that we might see at places like airport or maybe some good railway station or like that, that they have different bins, right, for different materials. For example, for organic, this is the bin. For paper, let's suppose, for plastic, for glass, for batteries, for metal. So these are the different bins. Then you can treat these bins as a categories. So we are saying this is a classification. Okay. I mean, this was not a proper machine learning example. This is just general life example, but you can say that this is a machine learning example. Okay. Okay. So Siddharth is saying number of ice creams sold is a discrete random variable. Okay. We are not talking about the random variable here. We are just saying it is just some number, discrete number, or the continuous number, right? I mean, if these are the fixed categories, you can treat those as a category also, but we will prefer them to treat them as a number. You will get to understand in a while that what do I mean by that. Okay. I mean, let's suppose if it is 500, you can treat from 1 to 500 or 0 to 500, you can treat those as a 500 or 501 categories also, but we will prefer to call them as a numbers. Okay. Not as a category. What do I mean by that? You will get to understand in a while. Okay, don't worry. So for this example, I can say this is also classification example. This is input where we are classifying this as a dog or cat. Okay. Now let's just do this exercise, which is regression, which is classification. Tell me, use a learning algorithm to predict tomorrow's temperature in degree centigrade or Fahrenheit. This is classification or regression. Predict tomorrow's temperature. This is definitely regression, right? What about this? Given historical data of two football teams, wins or loses, examine the statistics of two teams and predict which team will win tomorrow's match. So either team A or team B. This is definitely a classification type of problem, right? Okay. Now let's do one very important question. This will clear all of your doubt. Let's just answer this question, and I'm eagerly looking to all of you, at all of you, that who can answer this question very nicely. Okay. Whoever answers this question will win hamper. Although I don't have any hamper to give you, but yeah, I hope this is an offline class and I could have given any hamper to you. This is really a nice question which is formed by me, and just to make sure that you understand classification regression nicely. Okay, so let's just read out this question. Consider a scenario where the output has k possible levels ranging from 1 to k. Okay, I mean there are k categories. This is typically a classification problem, definitely, right? I mean, I'm not asking you whether it is a classification or regression problem because it is not of much of our interest now, because you probably can guess whether it is a classification regression problem. But can we treat these labels as integers and approach this as a regression problem? Is this recommended? For example, let me just give you the example here. Okay, for example, let's suppose you want to win, you want to check which team will win, right? Whether team A will win, team B will win, team C will win, team D will win, team E will win, or something like that, right? Let's just call this as 1, 2, 3, 4, 5. Okay, this is definitely a classification problem, but can we treat this problem as a regression problem, and can we try to predict 5 or 4 or like that? Okay, so one of the good answer, not definitely the answer that I'm looking for, but one of the good answer that Yashashvi has given is that the regression problem will treat this. If we apply the regression problem, then it will basically give you the floating point, which may not be integer. Definitely, there is a work around this solution. What you can do, you can take the seal of flow, right? So we can do seal of floor to work around here. But maybe there is some inherent problem with this, right? Anyone else? Okay, so Arnav Aditya is one of the student. He has given one answer which is probably the good answer if he can explain this more. Okay, so I mean, probably he is on the same line, but to understand whether he is definitely on the same line, I want to understand from his perspective that what does he mean. Can you elaborate more about it? Okay, just think about it. Can we treat this if this is, or maybe there's a, there's a vice versa also. For example, the same question in the vice versa, I can write our ice cream sales, right? Which means ice cream sales. What do you think? This is a regression or classification problem? Was regression, right? But can we treat this as a classification? Classification, assuming for our given data set, the maximum value never cross 100, right? Assuming maximum sales never cross 100 or 500, whatever, right? Okay, so basically it was a regression problem, but can we treat it as a classification problem? This is the question, right? And similarly, here also it is a classification problem, but can we treat this as a regression problem? Are you getting my point? So are you clear with both the questions? See, this question is clearly a classification problem. I mean, you have, 5 teams to predict, but can you treat it as a regression problem? Vice versa, in the sense that ice cream sales was clearly a regression problem, that, okay, how many ice creams you want to sell it? But can we treat it as a classification problem? That is the question, right? Okay, so let me just see that Arnav has written something. Arnav Aditya has written something. If integers are 1, 2, 3, then regression would try to predict the next one. Could be 4, but classification would take the number and assign it to the category. That's fine. I mean, if it is predicting 4, then you can definitely say that, okay, if it is going, I mean, there are workaround around it, right? I mean, if it is predicting 4, you can definitely say if it is more than maximum, let's just trim it down and let's just say it is just 3. There are definitely workarounds. Okay. Any other answer? Any other answer? So have you understood the question, by the way? See, some problems are by looking you can say, okay, this is a classification problem, this is a regression problem. But intentionally, can I make it as a from classification? I can treat it as a regression and apply the machine learning algorithm which are designed to be for regression problem. The answer is no. Okay. Okay, there are some answers. Let me just write those answers in the screen itself so that other people can read it later on. Okay. What I wanted to hear, I mean, maybe you people are slightly, I mean, right or wrong. I mean, there is a debatable things, but I cannot see what I want to hear. Probably because you have not, gone through the machine learning yet. Okay. Should I reveal the answer? Okay. Let's just see the answer. See, this is a classification problem. Let me just give you the hint. If you make this is a regression problem, let's suppose you treat these labels as one. Tell me, tell me, just I will just give you the hint and then you will immediately catch it. So just tell me, if I treat this as 1, 2, 3, and 4 and 5, tell me how many times this 5 is for this one. 5 times, right? Do you all agree? This one, and if you multiply 1 into 5, you will be getting 5. If you multiply or you add, or you, let's suppose, multiply into 2, you will be getting 4. If you add 1, then you will be getting this, right? So these things has mathematical relationship. 1, 2, 3, 4, 5 inherently has mathematical relationship, isn't it? Right? So if you try to, by the way, just tell me, do these have mathematical relationship? Okay, I'm calling it team A and I'm calling it team B. Do they have any mathematical relationship? No, right? No. So basically, what is happening here is that if you try to treat it like a one, like a mathematical one, okay, the moment you treat it, it will understand ki this has 5 times more weightage. E has 5 times more weightage than A. Okay. So basically, it will like if the Y levels are like that, that the numbers are actually the numbers. Matlab 1, 2, 3, 4, 5 are actually the mathematical numbers, not just category, not just A, B, C, D. They're actually the mathematical numbers. Then apply the regression. Here, although there are K categories, you can name them 1, 2, 3, 4, 5. Okay, team 1, team 2, team 3, 4, 5. Does this make them like a like the mathematical numbers? Do I intend to make them like the mathematical numbers? Or I'm just calling them just a category. Okay, this is team 1, team 2, team 3, team 4, team 5. Are you getting my point? See, if I want to make it like a mathematical number, right, then I will be using regression in the sense that I want to emphasize that, okay, this one and this two has the relationship, which means two is two times the number of this one, three is three times the number of the one, right? In that case, I will be using regression. But if I have just categories, in that case, I will be using classification. Is this clear to everyone? Why that is the case? Because there are certain, see, uh, by the way, you may be getting good results even though you use classification. And I mean, you, even though, let's suppose you use regression on this problem. Okay, let's suppose we are using regression on this problem. Do you get always bad results? No. Maybe you apply least square. Probably it is the case least square is also giving you the good answer. Okay, it is, but just by the coincidence. I mean, it is giving the good answer. I'm not saying it is wrong. Maybe it can give you the good answer. But is least square designed to categorize 1, 2, 3, 4, 5? No, right? See, in machine learning, there are certain algorithms that are designed for regression. That one of them you have seen as least square. In machine learning, there are certain algorithms that you probably have not seen, but we will see, are designed for classification. तो जिसका जो काम है उसको वो करने दो, ठीक है। यू कैन ट्रीट द क्लासिफिकेशन प्रॉब्लम एज अ रिग्रेशन और वाइस वर्सा। आई एम नॉट सेइंग इट्स रॉन्ग, इट मे गिव यू द करेक्ट आंसर, but it is not the job of that particular thing. For example, I don't know if I have good example or not. But let's suppose, uh, okay, that might be very bad example. Or to be honest, it just came to my mind. I don't know it is a good example or a bad example. But let's suppose you buy a car. What is the job of car? The job of car is to make you transport from one place to another place, right? I mean, you will travel from one place to another place. But you think, no, let's just use a car as washing machine. Okay, you just pour the water inside the car, you just pour the surfing powder, there's surf powder there, and then you just wash the clothes in the car. Can it do the job? Probably, right? हो जाएगा शायद, है ना? You can manage to do it. It's not like that you won't be able to do it. But is car designed for that? My question is this: is car designed to wash your clothes? Obviously no, right? So whatever is designed, okay, for example, whatever algorithm is designed for regression, let's just use it for regression. Whatever algorithm is designed for classification, let's just use it for classification. I'm not saying least square might not give. Maybe the pattern is such that least square may give you the correct answer here also. But least square is not designed to categorize 1, 2, 3, 4, 5. Are you getting my point? So whenever you see like a category, okay, these are the category kind of thing. These are not the continuous value ki one or two ke beech mein there is a relationship. Ki one is lesser than 2, 2 is lesser than 3. If there is no ordering, there is no relationship. And that is very much clearly visible, right? Whether it is a classification problem or regression problem. We have already seen few examples, and you were clearly able to tell me it is a classification problem or a regression problem. So you can definitely tell. It's not like it's very complex to think. I mean, it's very, very first thing. You can definitely tell given a problem whether it's a classification problem, regression problem. So whatever algorithm is designed for whichever problem, let's just use it for that. Okay, understood. Great. So basically, similarly in this particular question, ice cream sales was the regression problem. Definitely, it was a regression problem. It was clearly visible, right? But even if you use as a classification problem, you will say, okay, these are the categories. One is one category, two is one category, three is one category. These are the 500 categories I have. And I will treat them as a category. And then I will try to classify whether it is one, two, three. Probably it will do the job. I'm not saying it will not do the job, but it is more suitable for obviously regression problem, right? Because it is 500 times more, right? I mean, this has a relationship. You got it? So basically, if that numbers are having relationship, if the numbers are having ordering, then it is clearly the regression problem. If the numbers are just categories, it is the classification problem. Okay. So you can say since the nature of the problems are different, there are certain algorithms for classification, and there are certain algorithms for regression, right? We will see. So, oh, okay, or you can say, hence, we need to understand both of them differently, right? Okay. Is this okay to everyone? Great. Now let's just move further. So now you have your data, and there is a machine, right? For example, you have the image of cat, right? And the data is with you, which is in form of image, and then you want to pour this data to machine. But this machine will understand this data, although it is an image, but it will understand this data as a matrix. For example, for example, this is what you see, okay, as a cat, but this is what computer will see, which means for the computer, everything is just numbers. Okay, so these are the pixels for just a small part of this. These are the pixels for this. Okay, so this is what computer will see. And then given your data, okay, even though it is a matrix, computer will generally convert that to a vector, which means it will say, okay, if this is an image, let me convert this image to a vector. Okay, and then this is your x, and then probably your corresponding y. Okay, let's not worry about this multi-dimension, but yeah, let's not worry about it. Your corresponding y will be, can anyone tell me? It will be cat, right? You can say cat is 1 or 0 or like that. Maybe let's suppose there are two categories. You can say one of them is 1, one of them is 0, because ultimately you want to have numbers for the machine. Okay. So this is definitely a classification regression. What kind of problem it is? This problem is definitely a classification problem. Okay, great. Now, by the way, the more data you have, the better the things are, which means, uh, let's suppose this person is saying, this is your machine learning system. Okay, question mark. Then this person is saying, yep, you pour the data into this big pile of linear algebra, then collect the answer on the other side. Okay, so this person is saying that you pour the data here, and I will do something. Okay, and you can collect your answers here. What if the answers are wrong? This person is then saying, what if the answer is wrong? The person is saying, just stir the pile until they start looking right. Okay, so which means you have more and more data until it start looking right. So more data, the better the predictions are. Okay, great. So as I told you that today, and not just for today, on most of the lectures we will be seeing supervised algorithm, because that's a big chunk of the machine learning algorithms. Okay, so in the supervised setting, what do we have? We have x and we have y. For example, we have seen house prediction, and also which is a regression kind of problem. Or also, let's suppose whether it is cat or dog, it is a classification kind of problem, right? Classification is also supervised, regression is also supervised, but it is just that both have the different nature. So we will be having different algorithms for classification, different algorithms for regression. Okay, so let's see supervised learning paradigm. So what do we have here? We have x and y's, right? Which means that there will be the data, and corresponding to the data, we will be having some label. Okay, the label could be for the classification or could be for the regression. So what is our job? We want to understand, or we want to learn the function, let's suppose f, such that it almost give me y. Okay, such that it is almost giving me y. Is this understood, everyone? That our job is to learn the function fx such that we want to predict this y, right? So in supervised, this is the this is the setup, you can say. So how do we learn this function? How do we learn this function f? What we will be doing? We will be first dividing our data set usually into two parts. One is called train set, another one is called test set. And then we will train, okay, on this set. I will tell you about it. We will train on the set, and there will be we will be learning the function parameter using something called as loss function. Can you tell me what was the loss function in case of least square? What was the loss function that we have used? It was a squared error. Okay, or some people call it sum of a square error. I mean, because we were summing over all the data. Anyway, so the loss function was square error in least square. Okay, and finally we test our model parameters or model performance on the test set. So let's just first see what is a train and test set. right? So as you can see, whatever data we have, we will be just dividing that into two half. One is called train, or not half, basically two parts. One is called train, another one is called test. Train is like that. We will learn using the train set, and then finally we will evaluate on the test set, right? We will learn on the train, and then finally we will evaluate on the test. So for example, if this is the data which is given to us, then what we will do, we will split the data, and some chunk of the data we will call it test. Okay, we will keep it aside and we will train on this set. Is this fine to everyone? Okay. Now you might be wondering why we are doing so, right? I mean, why not we are making use of whole data? Can anyone answer me? Why we are not making use of whole data? Why we are even splitting the data? Yes. So we want to ultimately check how good or bad our model is, right? So what we will do, we will be testing on our model on the test set. So actually, we just don't want to train it. We also want to test whether it is good model or bad model, right? That's why we always have the test set. Otherwise you will never be able to evaluate it. Let's just see it more. That what do I mean by that? So train data is data used to learn the model. Test data used to access the accuracy of the model. Okay, how much accurate or how much efficient the model is. So the goal of the machine learning is to minimize the test error, which means what we care about is the test error. We want to have the less test error, which means it doesn't matter how you train it, right? Ultimately, we want to have the least test error. Okay, if someone is giving you the least test error, it is called the best model. Understood? So this is the goal of machine learning. For example, by the way, I've taken this slide from UBC. I think University of British Columbia, something like that. Okay. They have this midterm analogy. What they are saying, that like there is a training error, and or the train set, you can say, is basically that how do you perform on the, or how do you I think how do you do, okay, how do you do on the practice class questions? Which means if I'm telling you some question in the class, how do you do on that? This is like a train because your training is happening. But how do you do on the midterm? So we don't have midterm here, but yeah, I hope you understood. You can say it is a quiz or something, right? So how do you do on the midterm? It is just like a test error. Okay, you test. Goal is to do well in actual midterm, but not on the practice set. I mean, whatever you do in the practice set might not matter, but ultimately you want to do well in the midterms, right? This is our goal. Now, interestingly, there is a very important rule in machine learning, which is that even though we care about the test error, still you cannot use the test data to build the model. Which means while you are building or while you're training, you cannot use the test data, even though we care about the test error. Test error means how much our model do on the test set. Even though we are caring, right? You're getting my point. Even though we are caring about the test error, still we can't use the test data. Can anyone tell me why? Can anyone tell me why? I mean, why we can't use the test set while we are training? So yeah, most of you have given the nice answers. Probably you already know these terms. So basically, see, we although we care about the test error only, still we can't use the test data set. Reason being is that if I expose a test data set, okay, so it becomes the train, right? It automatically becomes the train. So basically, it is as if there is no test, isn't it? So if there is no test, then let's suppose, I mean, in the sense that let's suppose I'm exposing that test data to the model. I mean, to the training phase. If I'm exposing this data, okay, then there is no point on testing on it again, right? So it is just like a paper leak. Yes. So Ijaz has very nice, uh, you know, uh, analogy. It is just like a paper leak. Okay. So I also have the same analogy here. So minimizing the test error is not the goal, but it's a measure of how well we do on the new data. So basically, let's suppose, I mean, the test error is means, let's suppose you already, expose your model and you minimize the test error and you say that, okay, this model is good. So obviously this model won't do good on the new data, right? If you are having, let's suppose, new data, then do you think it will do good? Might not do good, right? Because you are learning only the things. Basically, I mean, you can say you have not tested this well, right? Because whatever thing you're testing it on, that you have already exposed it to the model while you were training. So it is just like you're cheating on the test. Understood? So this is the golden rule, that whatever is the region, whatever so happen, we will never ever expose this to our model while we are training. Once the training and everything is done, okay, once everything is finally fully final, okay, then you will say, okay, this is the model that we have. Once everything is fully final setup, then only we will test using the test set. We will never ever expose this test set to the model, okay, while we are training. So you might have seen the movie Thor, right? Have you seen this movie? When you test your model, you will see that your model should say that I have never met this data in my life. Okay. Or maybe instead of data, I think this was the person. I've never met this person in my life. Okay. So this is one famous dialogue from Thor. I think this was the third part of the Thor. But anyway, so your model should say this, that I have never met this data in my life. Yes, he's Loki. This person name was Loki, and I think he was meeting Thor, right? Loki or Loki, I don't remember the spelling, but yeah, he was meeting Thor only. So at that time, he said this dialogue that I've never met this person in my life. So anyway, like your model should say that I've never met this data in my life, if it is a test, right? So this is so true when you are testing your model, right? So I hope that is clear, that we will not expose, we will never ever expose our test set to the model while we are training. Okay. You might not be getting it fully for now, but don't worry, we will get to understand it slowly when we move further. Okay. How many of you are not getting it? Yes. Test will serve as unseen data. Test should be always unseen. Test should also always be unseen. Okay. It should be unseen. You should not expose this to the model. Never ever. Okay. Cool. Sometimes we also need, there is something called as validation. Okay. Sometimes we also need a validation set. We don't always need it, right? If it is simple, very simple model, we might not always need it. We will talk about the validation later on, but validation data set is only taken out from the train data, which means what will you do? You will keep the test separately. This is the first step. Okay, you will keep the test set separately, and from the train itself, you will do one thing. You will take some chunk of it and you will call it as a validation. Okay. Validation also, we don't expose it to the model while training. We use that validation set to tune hyperparameters. Okay. So what is the hyperparameter? These things will come later on. So don't worry about the validation set. We will talk about it later on, because currently you will not be able to understand. And whenever we need it, we will have it, right? So we will talk about validation set later. For now, don't worry about the term validation set. So we have test and train. So it is not always we need validation set. Sometimes we need it, right? Sometimes we need it to tune something called as hyperparameters, right? Let me know if that is okay to everyone. Okay. So this is Gate DA machine learning syllabus, right? The hyperparameters and okay, the hyperparameters and the validation set. This will come later on. What is the hyperparameter? It is actually not the real parameter that we are interested in, but it is something that came along the way. Okay, we will see this later on. Yes, so that is also a nice definition, that parameters that we need to set by ourselves. So as you can see here that we have, supervised, in the supervised learning, we have regression classification problems. And one of the first supervised algorithm that we have in the syllabus is simple linear regression, right? So for example, this is simple linear regression, which is the one of the very first algorithm in our gate DA syllabus. Again, the disclaimer is that this is not just for gate D aspirant. We will ensure that you learn machine learning thoroughly so that you can directly apply for the machine learning jobs if you want to. Okay. So don't think that it is only for gate DA aspirants. Okay. So you can just feel free to start as if this is your very first course, right? So now let's just start the very first algorithm that is there in the syllabus, which is simple linear regression. Okay. It is also called as linear regression in one dimension. Let's just see. Okay. So this is similar to, I'm not just similar, actually, this is exact thing that we have seen in the least square. Okay, this is exactly the least square thing that we have already seen. But now we will be seeing this in terms of the machine learning terminology. That's all. Okay. Instead of calling it least square, we are calling it linear regression. So, for example, you have x and y data, where x is, let's suppose, just a scalar, okay, and y is also, let's suppose, just a scalars. These are just scalars. Why? Because I'm currently considering one dimensional case. Our goal is to model the relationship between x and y. Okay. Currently, it seems like they are following linear relationship, and that's what we want to basically predict it, and we want to find the model parameters, right? So let's just assume. So here you can see the word assume. Let's just assume that the relationship is linear, which means this is our assumption. I mean, by looking at the data, you can do that assumption. That's not very hard to assume. Yes, if it is multidimensional data, then you can't just look at the data and you can't just assume or something, right? It's not easy to visualize if it is multidimensional. But for now, let's just assume that the relationship is linear between x and y. Okay. The line may not fit the data exactly, which you can see that this line is obviously not fitting the data exactly, in the sense that all the points, okay, all the points are not on the line. But we can try making a line a reasonable approximation, which means it is neither bad nor you can say not it is exact fit nor it is too bad. We should be having the best fit. Okay. So we can have the reasonable approximation here. For that, what we will be doing, we will be basically, let's suppose this is some line that we are predicting, then we will be saying that, okay, how good or bad this line is. For that, we will be saying that let's just have some parameter or some loss function, I can say, right, using which we will be telling whether this line is good or bad. So for example, if we are measuring this distance, right, these are the distances that we have here, and not just distance, these are the basically signed distance. So we can do one thing. We can have the either you can say you can have the absolute value of these things, or you can have squares, right? Yes. So basically, let's suppose this is some error or some mismatch that you are having. For example, you are predicting this value, but the actual value is this, right? I hope you are able to understand from the least square. So that's why I'm not going into too much of the detail. So here, let's suppose it is some E1, this is E2, like this, right? So we want to basically minimize this E1 square plus E2 square and so on. Great. So now let's just do this question. What they're saying: what is the correct depiction of linear regression error lines for x, which is in 1D, and y, which is also obviously in 1D? Okay, we are calling it by cap. Here, instead of calling it ax plus b, I will be just calling w. Instead of a, I will be using w. Right? That's the only difference. So here, instead of ax plus b, I will be calling it. Instead of ax plus b, I will be calling it w. So whether a is the correct answer or b is the correct answer? See, in A, we are having these vertical distances, right? These vertical distances. So this is what we do actually in linear regression. This is actual y minus bi cap, right? Whole square. So actual y is this, and bi cap is actually this, right? Bi cap is this. So yes, A is correct. But here actual y is this, and they're taking the perpendicular distances. Okay, this is the perpendicular distance. Okay, actual y is this, y cap is this is y cap, this is y, this is y, this is y cap. But they're saying you're taking something like this as y cap. Are you taking like this? In linear regression we are definitely not taking like this, right? Okay, so hence A is the correct answer. Understood? Let me know if there is any doubt here. So you can say this is vertical distance, this is perpendicular distance. In linear regression, we do vertical distance. Can we do perpendicular distance? Yes, you can modify the loss function. You can have the perpendicular distances, but in linear regression, we don't generally do it. Okay. Okay. Y and y cap in A. So this is y. This is y cap. Y cap is always wx plus b. I mean on the line. Okay. Y cap is always on the line. Here also y cap is always on the line. Right. This is the y cap. I mean, ideally we use in linear regression, but they are saying we use here, right? We don't use here, right? We use this corresponding to this x, we use this as y cap in linear regression, which is wx plus b. Understood? So instead of ax, I will be having just w. That's the only difference. So what is the loss function of linear regression? We will say it is sum of the errors, squared errors. Some people also take it mean, I mean the average, which is also fine. Okay. Some people also take average. Is this fine to you? Okay. So I mean, it is not an issue. I mean, if the earlier one you want to minimize, it will automatically get minimized or vice versa. I mean, multiplying the constant to any loss function is never the issue, unless the constant is negative. Obviously, I mean, if the constant is positive, you can always multiply the positive constant to any loss function. Okay, cost function. Yeah, you can call it cost. Uh, cost. You can call it cost, not an issue. Okay, cost function, loss function. I mean, people generally call it loss function. If you want, you can call it cost function. Okay, sounds good. So this is the loss function that we use. This loss function is called average, right? This since we are taking average, so this is called mean sum of squared errors or mean squared errors. MSE. Okay, mean squared errors. Because in mean the sum is already there. I mean, you can't take average without summing up, right? So this is called MSE, mean square errors, right? Which is actually 1 by n. In terms of summation, it will be y I minus y cap I. These are the scalars, right? So this is from I equal to 1 to n. And what is this I? Is the number of data points. So basically you can say n is number of. Is this fine to everyone? Yes, this is the average error. Okay. Yi is your actual output, which will be given with the data. Yi cap is our predictions, right? Now, we can, if you want, we can rewrite it like this. This is Yi. right? Is this fine to everyone? You can definitely modify the loss function as per your wish. Okay, it's not an issue. If someone wants and someone says that okay, I will be modifying, we will be anyway doing questions. With that, you will get to understand. Right? Let's just first understand the basics. Oh. So let's do a very simple question. Let me just ask you a very simple question. Given this loss function, which is in uh, W and B, I mean the parameters I want to optimize. So basically, the question here is that we want to given loss function. So minimize or maximize? What do you think? Obviously, we want to minimize. Don't worry. We will also see a good question just for the starting, right? We want to minimize definitely, right? Okay. Let's see the next question. So don't worry about the notations. The people might be using different notation at different places. For example, let's suppose there are only 2 points. Okay, instead of writing y1 as a subscript, they are writing as a superscript. I hope that's fine. Okay, it will be understood, right? By the given statement or by the given formula, it will be understood. So here they are using the superscript. Is this y2 is same as y square, y into y? This y2 is same as y square? Yes or no? No, right? It is just by two. I mean the second number example. So it will be understood, okay, by given formula or like that. Instead of L, they're using J, which is also fine. Anyway, so what they're saying, what shape in the objective function when we consider both parameters W and B? And this is the shape of the objective function, or this is the shape of the objective function? A or B? Let's suppose this is A, this is B. The objective function is in which shape? Is it A or B? Obviously B, right? Objective function is the squared. See, objective function is this one. Is basically in the W and B, right? So if first of all it has to be 3D. Why? Because there are two parameters, and one is for the J or one is for the L. So for example, let's suppose I ask you this: fx equal to x square. To plot this function, how many dimensions you will be needing? One for input, one for output. So there will be two dimension because one for output, right? So x square will be something like this. Okay. Similarly, to plot this function, let's suppose, right? To plot fx y equal to x square plus y square, how many dimensions I will be needing? Here I will be needing three dimensions, right? Here I will be needing three dimensions. One you can say x, one you can say y, another one you can say fxy. Because input two dimensions and then one more dimension, right? Okay, something like this function will be there. So similarly, here first of all we will be needing three dimensions. So A is never the answer because WB two dimension and J or the L will be taking one more dimension. So it will be something like this. It will be a quadratic function. Okay, understood? Let me know. So this is the answer. Okay, so B is the answer. Okay. So as you know, the loss function will be given like this. What is the n here? What is the n here? N is, can anyone tell me quickly? Number of data points. Yes. So I'm not much interested, but yeah, you can do the differentiation with respect to B, right? and you can just equate it to 0. Since it is scalar, it is not a very complex. You can do it. I mean, if it is needed. So you can do the differentiation and then you can equate it to 0, I think. Yeah. So B will come something like this. So let me also paste it there. Okay. So B will come maybe B star. So they are saying it is average of y minus w into average of x or something like this, right? I mean, let's not worry about it. You don't need to remember it. Okay, don't worry. You don't need to remember. I'm just saying that, okay, you can do this. And this average they are representing like by bar, which is also fine. Now you can solve for w also. Before solving for W, I think they have put the value of B because there is no B here. By the way, whenever we get the optimal answer, people like to represent it as star. Okay. I mean, star means ki this is the answer we are getting. For example, if fx equal to x square is a function, can you tell me what is the f dash x? It will be 2x. Equating to 0, what you will be getting x as? 0. So x equal to 0 is a minima, right? So since it is, final answer, we people call it x star. Okay. The optimal answers, people call it x star. I mean, just like to put just this is just one of the notation that some people use in the machine learning. Is this fine to everyone? I mean, the final answer, whatever we are getting, it is no more variable. I mean, it can't take any value. It is a fixed value, which is x star. Okay. So anyway, you can put the value and you can also find out the W star or W by differentiating it to be 0. Right. So everything is scalar here. It is not a complex calculation, and also we don't need it much. So that's why just for the sake of completion, I'm having it, but you don't need to remember it. Okay. If needed, you can do it by your own. If needed in some question, if needed, then you can do it by your own. Okay. Let's do this question. What they are saying. This question I have taken from MIT. Now in this question they are saying let's consider a regression in one dimension. So our inputs. Okay. Again they are using superscript, which is also fine. And output are in a real number R. Linny, maybe some person name, uses a regular linear regression given the following data set. So, for example, the data set is like this. For x equal to 1, y is 1. For x equal to 2, y is 2. So, this is 3, this is 4. If this is 3, then this is 2. Oh, for 3, they have 2. And also 4 also. Not an issue, which means there are two data points. For x equal to 3, one of them is here. For x equal to 2, 4, two data points, just one above another, which is fine. Okay, not an issue. So what they're saying, what value of theta? I mean, generally we call it w, x, and b, but here, as you can see, they are calling it theta and theta naught. So this theta is b as per our notation or w as per our notation? Can anyone tell me? As per our notation, this is w. As per our notation, this is b. Okay. So they're asking the value of w and b given this data set. Can you find out what you need to do? You need to do all the calculation. For example, let's just first represent this data. Okay, just for the sake of fun. This is, let's suppose, x, this is y. Let's just see what they are trying to uh, solve. Okay, for x equal to 1, let's suppose this is 1, this is 2, this is 3, this is 4. Y is also from 1, 2, 3, 4. Okay. So this is x equal to 1 and y equal to 1. There is one point here. X equal to 2 and y equal to 2. There is, you know, another point somewhere here. X equal to 3, y equal to 4. Okay, somewhere here. X equal to 3, y equal to 2, somewhere here. Okay, these are the points that they are trying to represent or trying to learn the linear regression line, right? Okay. I mean, we can definitely solve. But what does your intuition say? I think, I think if we take from mid of this, I mean, that will be the number. This is 3, right? 3 and 3. I mean, there is no point at 3, 3, but I'm just saying. So if we take it like this, see, this is the 1, 1, this is 2, 2. So if we take something like this, Okay. Probably it is the best line. What do you think? Probably. Because there will be a error. How much error it will be? There will be the error for this point. What is the square error? For these 2 points, what is the error, by the way? For these 2 points, what is the error? 0. For this point, what is the error? This will be, I think, 1 vertical distance, just the vertical distance, right? This will be 1. So 2 will be the error. 1 square plus 1 square. I mean, this will be 0 and 0. If I take this line, I'm just hypothetically saying, then 2 will be the total error. Total error. If you want to take the average, then you can obviously divide by 4. Okay. But if you take from somewhere else, see, the intuition is like this. If you take from somewhere else also, then do you think you can minimize the error? See, the thing here is that if you take from somewhere else, wherever you take, you will you will be having some error here, some error here. That's the extra error that you will be having. But this and this will anyway be, be getting added, which means if something is more than one, then it will be less than one. I mean, if something is less than one, then another thing will be more than one, isn't it? So ultimately, if this is, let's suppose, 0.5, if you are able to make it 0.5, it will be 1.5. Because ultimately the sum is, what is the sum here? I mean, the error, the absolute sum will be 2, because the distance between these two is 2, right? Since the distance between these two is 2, if you're able to make this as 0.5 square, the other one will be 1.5 square, right? Do you agree? So if uh, let's suppose, the distance is 2. So I, I think in calculus, how many of you studied? Let's suppose this is A, this is B. I think one symmetricity, I told you that if you want to minimize A square plus B square such that A plus B is fixed. Okay, A plus B is, let's suppose, some fixed number, which is here 2. Then it will be minimized by the half and half. How many of you know? Have you seen in the Rolle's theorem, after Rolle's theorem, I think I told you something that if you want to minimize, I'm just telling you, if you don't know, that's fine. If you want to minimize A square plus B square such that A plus B is some fixed number, let's suppose here this is 2, then the minimum will be always at the half, which means A equal to B equal to 1. Okay, this is the point of minimum always, which means the 1 square plus 1 square is the minimum, which is 2. You can try anything else. For example, you try anything of your choice. Let's suppose you try 0.5 square plus 1.5 square. Can you tell me what it will be? It will be 1 by 2 square. It will be 3 by 2 square. Okay. It is 1 by 4. It is 9 by 4, which means it is 10 by 4. What is this? 2.5, right? So it is more, or this is more? Definitely this is more, right? So actually you can try with any A and B. Okay, it will be minimized at the half. If the distance is fixed, then if, let's suppose, if this distance is fixed, is the A plus B is fixed basically, then the minimum will be always at the half. I mean, whatever function you have, if it is a symmetric function, okay, if it is a symmetric function, the minimum will be always at the half. uh, in graph theory also. Okay, you are not from computer science. Sorry, I forgot. Okay, I was giving you an example of graph theory. There is one theorem of. Actually, I also forgot, but in graph theory also there was somewhere we need it. Okay, this kind of thing. Anyway, I'm just telling you from the intuition that it will be this. If you want to have this minimum, okay, then it will be at the half. So basically, obviously, you want to if anywhere else you take it, right? Anywhere else you take it, then this error will be anyway more, right? Do you agree with me? Let's suppose you agree. Okay, let's suppose you don't know that, you don't know this, right? Still you just believe me that this is the case. We can obviously prove it, and we have proven this in the calculus also. But anyway, let's suppose you don't know this. Okay, in the calculus, in the even in the module 1, in the module 1, I think we have proved it, if I remember correctly. Okay. Anyway, so let's suppose even you don't know this, and you just believe me that it will be minimized only at the half. So suppose you have 0.5 here, 1.5 here, then obviously it will be more. This 0.5 square, 1.5 square, it will be more, and extra will be these also if you take from somewhere else. Do you agree with me? Extra will be, these are anyway extra. Earlier, these are zeros only. Earlier, these are zeros. And this is also minima. So if you take from somewhere else, anyway, you are increasing the a square plus b square. The total of this you are increasing. Also, you are anyway incurring this much extra error. So obviously, this has to be the best line without even calculating it, right? It has to be the best line, because anywhere else you take, this is you are increasing, this you are increasing, this total you are increasing. It might seem that okay, you're decreasing here, but you're more increasing here. Okay, you're more increasing here. So this is the best line. If you want, you can do the calculations also. So how to do it? Assume that best line is wx plus b. Then with the first, what is the error you will be getting with the first number, which is 1 and 1? So y minus y cap. This is our error. So what is the first error? So for I equal to 1, by I is 1 minus x I is 1, w plus b whole square plus 2 minus x is 2, 2w plus b plus 3 minus x is, sorry, 4 minus x is 3, and then 2 minus x is again 3, right? So you can do this, then you can differentiate it, you can try to minimize. Ultimately, you should be getting what is the best line w? So it is just y equal to x, right? What is the w here? What is the b here? 0, right? So ultimately, you should be getting this. Let's just see the answer. Okay. So this is the answer. I mean, obviously, we will be having the better ways to solve it. Even though you don't have the intuition, you let's suppose don't know the things. We have the better ways of solving this instead of having this much mess. Okay, don't worry about it. But is this fine? Is this question fine to everyone? That what they are trying to ask? Okay, so this is in just one variable, and this is almost, or in fact, this is exactly same as the least square we have already seen, right? Now, as a next step, let's just do one thing. To get more confidence and to understand this thing with respect to the machine learning, which means how the data is playing the role and the other things, right? With respect to the machine learning, let's just do the one thing. Let's just solve many questions for simple linear regression, right? So that you get to understand the things more. And obviously, the questions won't be the calculation based. I mean, the questions won't be just asking you for W and B. Okay, those are the questions which will be focused on the machine learning point of view, right? So we will be solving more questions or many questions with respect to the machine learning, not just with respect to the calculus. Okay, this was the algorithm that we have seen just now, and also in the least square we have seen that, oh, okay, how to calculate for W. For example, you can definitely solve for W and B, right? Let's suppose this is L, by taking the derivative with respect to W, by taking the derivative with respect to B, and then you can definitely solve for it. But our aim is to not just have some calculation. Our aim is to understand the machine learning. So let's just have more questions or many questions for simple linear regression, which are aimed to understand the simple linear regression with respect to machine learning. And then we will move to multiple linear regression, okay? Or multivariate linear regression, whatever we call it, right? We will, don't worry, I will make sure that this topic is 100% understood, okay? Not just even 99%, 100% understood before we jump into multiple linear regression. And obviously, here also, we will be having very good intuition, very good questions here at the multiple linear regression before jumping to any other topic. So, honestly, I've already prepared the questions, but since the time is over, so that's why we are not having that in today's class. So we will be having those questions tomorrow. Okay. I already have those questions here. Yeah, thank you so much, Sumaya. Okay, thank you everyone. Thank you so much. Thanks for watching. If there is any question, just let me know. Okay, so one of the student was asking that how do we actually solve for these parameters, right? For example, here we need to solve for W and B. So actually we have done this in the previous classes. So for example, if you go to this particular lecture, right? So here we have solved for A and B. The similarly, we will solve here also, which means you can just simplify the loss, which is or the error. Okay, and then you can just do the differentiation with respect to A and with respect to B. In this case, it will be W and B. Okay, that is the only difference. So we have already done this in the previous classes. You can just refer to this question and just see that how we do it. Okay, it is very easy. You just need to simplify it and then finally find out the A or B, or maybe in this case W and B, right? Okay. So thank you everyone. Thank you so much. Take care. Bye bye.